Hello, everybody on Zoom. Hello, everybody in the lecture hall. Today, we are going to wrap up this lecture right here about the queries with SQL. And then we'll start with something more advanced that's called database design theory. Sounds very fancy, very scary, but we'll see that there's plenty more things that we can investigate working with relational tables. Before we start, I have a question for you on the clicker, and then we'll move on. So here you go. I'm asking you what this thing is. Is it an inner join combined with two selections in the terms of the relational algebra? Or is it an inner join followed by a selection and projection? Or is it a full outer join combined with a selection and projection? Or is it a natural join combined with a projection? Let's look at your answers. Oh, we have a majority. And it turns out the majority is correct indeed. So how do we see that it's an inner join? Well, because that's the default. If you just say join, you basically get an inner join. It's not a natural join. Why? What would be a natural join? Maybe somebody on Zoom. What would it look like if it were a natural join? I know we just moved over to winter time, right? So, okay. So a natural join means that you would use the same attributes on both sides, right? Same attribute here, same attribute there, and you join on them. This is a natural join.
So it says PID equals S dot product.
Exactly. This is why it's not natural, right? It's a theta join, basically. So we join on different attribute names. PID, by the way, it's very common to do this in databases. PID actually means product ID. So it's very common to use the first letter of whatever you're referring to, and then ID, which is a common name for a primary key, right? It's whatever identifies a product. For example, it could be a serial number, a part number, could be a social security number for people, and so on. So whenever you see a letter ID, then this is typically a primary key for a table, and then the foreign key that would be in the table S has a different name. Okay, but this is why it's not a natural join, but it's an inner join. Full outer join, no, because then it would say full outer join instead of just join, right? But then we still need to distinguish between selection and projection, or two selections. Here, what's very important, I repeated it many times, and I know it's confusing, the select clause is not a selection. The select clause is a projection, exactly. So the select clause is a projection, and you see after select all of the projected attribute, it's disambiguated with the name of the table, right? We have the table alias P for product and S for sales. And then that way you say P.name, P.price, you know that this is coming from the products table, and S.discount and S.customer, you know that it's coming from the sales table. Now, in general, it might be you don't need these table aliases, right? Because if the attribute names are different on both sides, you don't even need to use the aliases and P. and S. right? But somehow it also makes it more readable. I mean, imagine you look at this query without even looking at the tables, you already know that name and price come from the products and the discount and customer come from the sales. So this is also for readability that it's a good idea. And the where clause is a selection. Yes, exactly, right? So this is why we have a projection with the select clause and a selection with the where clause. All right, very good. So that was a good wake up. And now we'll move over again. To the slides. Okay, so where were we? We studied a lot of SQL. We studied the clauses. We saw a lot of them. First, before the join, we saw, let me try to have them in the right order. We saw that the clauses are select, from, where, group by, having, order by, limit, offset. Learn this by heart. It's always that order. Some of them might be optional, don't have to have all of them, but it's always select from where, group by, having, order by, limit, offset. Then when we looked into the joins, we noticed that the joins are not an additional clause like the other clauses are for grouping and ordering, but instead the join is done within the from clause. So within the from clause, you can actually specify multiple tables, comma separated for just the Cartesian product, or you can add this join between the two. You can give table aliases, and we saw you can have inner, outer, left outer, right outer, full outer, and so on and so on. So this is where we stopped at the end last time, right? We saw that we can do these joins in from. We also saw that there is a way to do joins without using the join keywords. And this is by just putting the two tables in the from clause and by putting the join predicate in the where clause. Do you remember that? It's basically doing the Cartesian product followed by a selection, but that's the same thing as a theta join. And it's not going to be slower because the database engine is super smart. It will figure it out. If you tell a database engine, select from two tables where and some predicate on the two tables, the database engine is just going to notice this is a join, even if you didn't specifically said it's a join, right? So from the perspective of the user, it doesn't matter which one you use. It's just going to work in any case. What you should know too is that the predicate of the join can be many things, right? We saw you can use arithmetics, logic, comparison, smaller than, greater than, equal, and so on. But in 80% of the cases, what am I saying 80, maybe even in 99% of the cases, the join is going to be an equality, the join predicate. You're joining on an equality between two attributes. It's rare that you would use a join on a smaller than or equal or greater than or equal. This is really not something that happens a lot. So when you join on a predicate that has an equal sign or using, which is just a shortcut for that, for the equality on both sides, this is called an equijoin. That's the name for that. An equijoin is the specific kind of join based on an equality. Why did we give it a special name? Well, simply because we know how to execute equijoins super efficiently and super fast, right? Any database engine is going to be very, very, very good at evaluating an equijoin. Yes?
Would it also be an inner join by default? Not sure which.
Yes, if you just say join, it's inner join. If you do it, since we have the using here, it's going to not be quite a natural join because it might not be all the attributes they have in common. So that would be considered a theta join. But yes, I think I have a slide. Let me ignore this slide. Yeah, exactly. I'm just going there. This is what I want to show. Maybe this clarifies on your question. This is just to clarify what you mean. So in gray is what is implicit. And in bold blue is what you say in the query. So how to understand this? Cross join is the default. If you don't say anything and just put a comma, that's a cross join. That's also known as Cartesian product, right? If you say join, it's an inner join. So inner is implicit. You can say inner join, but even if you just say join, it's going to be an inner join. If you say left join, it's a left outer join automatically, right? From the moment you add left, it's an outer join, left outer join. right join would be right outer join. You can also write left outer join completely if you want, right? And if you say full join, that's a full outer join. Who remembers the difference between left join and right join? Left outer join and right outer join? Maybe on Zoom. Anybody remembers the difference?
Changes which null columns are added.
Exactly. That's exactly what it is. On the left join, you're basically keeping everything from the left table, even if there is no match on the right, and you're just filling everything with null that you're missing. The right join is the opposite. You take everything that comes from the right table, even when there is no match on the left, and you fill the left part with nulls for those. And full join is on both sides. Inner join means if there's no match, you just discard it. You don't include the tuples without match. Okay, does it answer your question? After a timeout of 10 seconds, we assume yes. Okay, let's assume yes. Okay, all right. So oh yes, awesome. Thank you for confirming. So we left here, and now I wanted to show you the concept of self-join. And here we're actually going in recursion kind of things. Because right now I showed you two tables and we joined on the two tables. But what about a table that refers to itself, right? Where you have the foreign key pointing to the same table's primary key. So here's an example where I picked the Star Trek spaceships, and I have this successor attributes that is basically pointing to the succeeding spaceship. So after Enterprise A, there was Enterprise B. After B, there was C. After C, there was D. Enterprise was the first one, so the successor was A, and the successor of D is E, right? So basically what's happening is that this successor column right here is pointing to the code column, right? So for example, if you take Enterprise A, that's the code of Enterprise A, the successor is NCC 1701B. This is a foreign key pointing to the primary key right here, to this one, right? So you probably see that here, the foreign key and the primary key are in the same table. This is what we call a self-join. So how do we handle this? Well, here we need table aliases. If you don't put an alias, then you don't know if it's the left or the right, right? So you're basically taking here twice the same table. You see spaceships and spaceships. It's twice the same table. Just give it a different name on either side, so S1 and S2. And then you're joining on the fact that the code of the successor must be equal to the successor field of the predecessor. For whom is that clear? I don't see a lot of raised hands. This is scary. Okay, let me give you another example then, which would be the same. Think of a genealogical tree. Imagine that we have people in there, and we have a column that says parents, right? And when you follow the primary keys, so there can be multiple of them, but you take parents, it refers, so for example, you could use the social security number, then it points back to the social security number of the person, right? So this is how, if you have a person and a person, the way you join to establish parentship or children, you basically use the same table for the primary key and the foreign key. For whom is that clear? Not entirely? I will let you digest maybe even offline. Let me show you more examples of the sort of things we can do. So here, for example, I would like to see all the pairs of predecessor successor. So for example, we see in the first row that the former was Enterprise and the next one was Enterprise A. Maybe there was some ceremony on that day that Enterprise A took over Enterprise. Then we saw that on the second record that Enterprise B succeeds to Enterprise A. Maybe there was also another ceremony and so on. But the way we obtained that is that we joined the table with itself in such a way that we are linking the two records. So in the first case, for example, the first record that you see right here, so Enterprise A, how is it built? This one. Well, you have a match between this record right here on the value of the successor here, B, which is a match against the second record here as the code, right? So you're matching this with this. If you put the two tables together, what you get is if you just did the intermediate computation without the projection, you would get a table with 10 columns. You would get S1 warp, S1 name, S1 last name, S1 code, which would be A, for example, and S1 successor, which would be B. And then you would also have the 6th column S2 warp, S2 name, S2 last name, S2 code, S2 successor, right? So you have a combination of 2 spaceships as 10, 5 times 2, 10 attributes. And what you're doing here is that you're projecting because all you want to see is the names. So you pick just 2 of these 10 columns, the name of S1 and the name of S2. And S name was the former one, that was enterprise A, and S2.name would be enterprise B. So that would be this line right there. Okay, for whom is that clear? Okay, this is getting advanced, right? The ability to join a table with itself. But as you can imagine, you can do genealogy with that, for example, genealogical tree. Okay, so.
We have a question. Shouldn't be the domain of former and next be varchar 30 instead of varchar 20?
Oh, yes. In fact, I think I corrected it and somehow it just wasn't taken over here. By the way, there was a mistake last week that it was integer for the code. I replaced everything with varchar 30. It should be uploaded that way. And either here, it's just not fully up to date, this one, and otherwise I'll update it. I'll basically put varchar 30 everywhere, right? I'll put here, 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 and here. I just put varchar 30. Right. Okay. Okay, but the other slides, there should already be fixed and online, right? What you discovered last week. Okay, so this is it for the join. I pushed maybe your comfort zone a little bit with the self-joins and the recursion and so on. So you see it's already advanced, but this is it. Okay, now let's move on to another kind of operations. Remember the set operations? Who can tell me again what the 3 kinds of set operators were? What can we do when a table is a set of maps? What sort of things could we do at the set level? Anybody remembers? Yes, maybe the microphone.
Union, intersection, and subtraction.
Exactly, these are the big 3. Union, intersection, and subtraction. So you might remember that union basically, you know, tables are sets of maps if we use the set semantics, right? So we just do the union of the sets. Then you have all of the records coming from both sides. So let me start with the union, right? And then we'll also go to intersection and subtraction. Here's how it goes. Let's say we have these 2 tables and they have the same attributes, they have the same domains and so on, and we want to union them. Well, the SQL keyword for that is, guess what? Union. And this is how it goes. You basically select everything from spaceships 1, right? So that's table 1. And then you have select everything from spaceships 2. And you have this union in the middle. And what you get is the union of the 2. So you might notice that these are only, how many tuples? I need to use this trick to remove the toolbar here. There you go, you have 5. There was a duplicate elimination. You see which duplicate was eliminated? There's the C is on both. You see, there's enterprise C is both here and here. So it would be 6 if you didn't eliminate duplicates, but since we have sets, there's only 5. So this is the union of the 2 here. Who is following this? Right, it's just a union. Okay. Then we have the intersection, which is the same thing, just using intersect. So in that case, there will be just C, which was the only one that was on both sides. So here we have enterprise C right there. And finally, subtract. Well, it's not called subtract in SQL. They call it except, but it's just a matter of knowing it's a different word, except. And then you get A and B, right? But not C. Why not C? Because C is there. That's the definition of set subtraction, right? You remove everything that's from the right side. Okay. Okay. So this is union, intersection, and subtraction. A few words here. On both sides of union, you need the full-blown select from where things, right? You need a select. You cannot just write spaceships 1 union spaceships 2. You can also not write select star from spaceships 1 union spaceships 2, right? That doesn't work. You really need to do the union of 2 full select expressions. So the way that you should parse this in your brain is that there is this select star from spaceships 1, there is select star from spaceships 2, and you're unioning the two. That's how to parse it. Okay, and the same goes for the intersection and the subtraction. Something else that you need to be prepared for, it's a bit fishy, is that when you have the theory of the union of two sets, the order of the attributes shouldn't matter, right? Normally, it shouldn't matter. In PostgreSQL, it's not quite like that. If I correctly remember, PostgreSQL tends to be a bit order sensitive with the columns. Maybe if you have a chance to experiment, Andrea, and confirm, but I think in PostgreSQL, if you define the schema with a different order of the columns, then I'm not quite sure PostgreSQL is not going to complain about that, right? But again, that's part of the real life, right? You have the theory with the beautiful math, and then you have the real life implementation, and you have to be prepared that sometimes you might have a few discrepancies, right? So this is why here I carefully drew the attributes in the same order. If you use unions, intersections, and subtraction in practice with a SQL database, it's a good idea that you also use the same order of the columns, right? I know it's unfair; it shouldn't have to be, it shouldn't matter, but in the real life implementations, that tends to be considered. Okay. Who is still with me? Okay, I'm taking it a bit slowly, as I assume we start a bit slower and I slowly accelerate. So now you know how to do union, intersection, and subtraction of two tables that have the same schema, right? Right. Now, it turns out that if you don't like set semantics and you want bag semantics, remember that bag semantics means that we accept duplicates. It is possible to do that. It is possible, and it's magic, because all you need to do is add this all in the middle. If you say select star from spaceships 1 union all, select stars, what happened on the right, that's just a typo, it should just be spaceships 2. So select star from spaceships 1 union all, select star from spaceships 2, then you get the duplicates, right? Union all is going to deactivate the elimination of duplicates. So now you see enterprise C happens twice. It's twice the same record, but in bag semantics, this is fine, right? And PostgreSQL is going to keep the two records. Okay. Okay, so this is what I wanted to show you with the set operations. And now we are going to finish the parts on SQL by pushing it to the next level. You remember that when I explained the notion of first normal form and the atomic consistency, I explained to you it's like this Inception movie, a dream in a dream in a dream in a dream, and then you can have a table in a table in a table in a table, or you can forbid it. You can forbid that you can nest a table in a table. It turns out that in the same way that you can have a table in a table in a table, in a query language, you can also have a query in a query in a query in a query, right? And this is kind of cool because then you can really take SQL to the next level where you have a select from where, nested in a select from where, nested in a select from where, and so on and so on. And that's also the case if you're in the first normal form, if you have atomic consistency. Because the nested queries are super powerful for many use cases, yeah, let's look into that. You will understand. By the way, I think I said first normal form instead of atomic consistency. It's just a synonym. It's an alternate name for that. It's also called first normal form. And why it's called first, we'll see very shortly in the next section, database design theory, because there's others. There's a second, a third, and so on. Okay, but let me show you the nestedness. So in order to understand how in SQL you can put a query in a query or a select from where inside a select from where, you need first to understand that in SQL, you manipulate two sorts of things. You manipulate tables, of course. When you do select from where, you're basically creating and manipulating a table. But you also manipulate scalars, because when you have in a where clause, you say something equals to something else, you're not referring to a table equal to a table. You're referring to a value equal to another value, right? An atomic value. So you need to be very aware that you have tables on the one hand and the atomic values on the other hand. There is a fancy name for these atomic values. We love to call them scalars. it's actually, I think, the same term that is used for vector spaces in mathematics, right? You have the vectors and you have the scalars, right? So the vector would really be the actual row, and the scalar is just some number that you can use to multiply and make it bigger or smaller, right? So we also call them scalars. Who is aware of scalars in vector spaces and so on? I guess some of you are right. So that will be easy to remember then the name of the scalar. Did we have a question on Zoom, or I saw something pop up? No? Okay. Okay, for whom is that clear? We have these two things. Okay. Then in SQL, there are expressions that manipulate tables. This is the select from where, join, and so on. You get a table in, you get a table out. And there are expressions that manipulate values. Addition, multiplication, equality, inequality, and or taking the sign of a number, a date, and so on. So these are called value expressions. Where do you find the value expressions? For example, you find them in the where clause, but you also find them in the select clause. When you define new columns with the extended projection, you might have some complex formula on values, and then and then the name of the new column that you compute, right? Okay, so you have expressions that work on table, typically select from where, and you have expressions that work on values, arithmetics, addition, multiplication, comparison, and so on. Who is with me? Okay. So now you need to understand, once you have seen their stable expressions and value expressions, there are not so many things you can do, right? You can have a value expression inside a value expression. You can have a value expression inside a table expression. You can have a table expression inside a value expression, or you can have a table expression inside a table expression, right? So there's 4 combinations, and I'm going to show you in SQL what it looks like for each one of these 4, the sort of things that you can do. You'll notice that some of them we've already seen, by the way. A value expression into a value expression is easy. When you say, for example, 1 times 3 plus 4 times 2, this is value expressions in value expressions, right? 1 times 3 is a value expression, 4 times 2 is a value expression, and you nest it into a bigger value expression with a plus in the middle. So this is the trivial part, right? Here's another example where you have 3 and 4 that are 2 strings. This is the concatenation operator. It's going to build a string with 3, 4. Cast 3, 4 as big int will give you 34 plus 2, 36, right? So you have a value expression nested in a value expression, nested in a value expression, right? Like a dream in a dream in a dream in a dream. So this here should not surprise you, because that's the sort of things you already see in primary school when you have addition and multiplication and so on, right? So this is the easy part. Next, if you nest a value expression into a table expression, there are 2 places where you can do that. You can do that in the where clause. This is typically where you have value expressions working on scalars. This is a scalar. This is a scalar. It's whatever value there is for a record in that column. This is also a value expression, right? This is a first column. You don't give it a name here, but it's a concatenation of name. You add a dot at the end. And then there is another column we create by taking what was in H plus 20. So this is a value expression. This is a value expression. This is a value expression, right? So you can have them in the select clause when you create new columns, and you can have in the where clause when you filter on predicates. And by the way, you can also have them if you join on the on part of the join, right? You remember that when you join tables, you can also specify a joining predicate. So that's yet a 3rd place where you can have the value expressions. Okay, so this is, in that case, a value expression, 3 of them actually, nested in a table expression. Until now, there's actually nothing new, right? Because this is the sort of things we've seen before, right? I'm just now explicitly saying that we are nesting value expressions in value expressions, or that we are nesting value expressions into table expressions. Okay, that was the easy part. Now comes the fancy part. What about nesting a table expression in a value expression? Sounds impossible, right? How can you fit a table into a scalar, right? Doesn't seem right. But in fact, you can. And in order to understand this, you need to make an observation. Imagine that you have a table that has exactly 1 row and exactly 1 column, right? So a single record and only 1 attribute. How many values are there in that table? How many scalars? Just 1, right? Just the intersection of that row with that column. So this is an example of table with 1 row and 1 column that contains just 1 single value. And in fact, we can consider by some mathematical magic that when you have a table with one row and one column, it's kind of the same as the value itself, right? So when you see a table with one row and one column with foo inside, you kind of say, okay, it's the same as just foo. Who gets that? Okay. In math, I think it's called the canonical identification or a canonical injection of the scalars into the tables, right? For those of you who are familiar with these terms. So any scalar can also be seen as a table with just one row and one column. Why is it important? Well, it's important because this is the sort of things you can start doing. Imagine that you have select max warp of the spaceships. You're just looking for the maximum value of the warp column. Notice that here we don't have a group by, right? If you use the aggregation like max without a group by, you're just doing it over the entire table. So in that case, you will just get just one value. It's just the maximum value of the entire table, which would be 9.975, right? So if you do this query, select max warp from the entire table spaceships, you get a table with just one column because you have only exactly one in the projection, right? In the select clause, you have the projection. So you have just this one column, the maximum of the warp. And then you have from table spaceship, there's only one maximum. So you get also just one record. Who understands that this query gives you that? Okay. So now what I'm saying is that since you have here with this query, you generate a table with one row and one column, you can kind of consider it a scalar. It's just as if it were a single value. So the super cool things that you can start doing is this. Since you established that this query gives you one row, one column, it's like as if it were a single scalar, a single value, then you can start using value expressions. So you can here build that table and multiply it with 1.001, right? The only reason that works is that the table has one row and one column. If it doesn't, that's going to break, right? But if it has one row and one column, you can nest a table expression, select from blah, 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 inside a value expression, right? So this would be the table. And then you basically unbox it. So that's just that number multiplied by that. And if you want to put it back into a table, then you can as well. I will show you how. Okay. For whom is that clear? So we did something incredible. We actually put a table expression, a select from where, inside a value expression, right? What that means is that you can put that sort of select from wheres inside a where clause or even inside the select clause, just like you would put a value at the same places you would put a value. This is super useful in SQL to be able to do that. Yeah.
There's a question. This only works for integers and numerics. Is that correct?
I think it was for anything. Probably work. You can check if you want. I think it works with any atomic value. You could use, for example, string concatenation instead of multiplication, and then you get a string on the left and concatenate with something. Yeah. I would say I'm 95% sure of that. And we can check with PostgreSQL that it works with anything, even a date or, a binary. Okay. Oh, I see your question, but a string multiplied with a number. Well, here it's like in any programming language, right? The same goes in Python and in Java. If you try to multiply a string with a number, then you're going to get errors. So yes, absolutely. If you try to do that sort of things, multiply a string with a number, then you're going to get probably an error, right? But this is not specific to SQL or databases, right? The same is going to happen in pretty much any language. The computer is going to complain that you're trying to use operators on values that don't make sense. Did it answer your question? Yeah, all right. Okay, so we have value in value, value in table, table in value, and now we need table in table. So how do we get table in table? Well, here's how. You can nest a table expression inside the from clause, right? So you can have a select from where, blah, 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 in a from clause of another select from where. Right. So in that case, it means you create a table with this inner select from blah, 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 blah. So that creates kind of a temporary table, right? This right there is a select from where. And then you can take it as a table that you can again work with. So what's going to happen is that in that case, these are tables that are stored in PostgreSQL that you call by name, right? So sorry, this one and this one, you call them by name. But in this bigger select from where, you're not in the from clause using a stored table that you call by name, you're using a temporary table that was generated with a select from where. So it's like a Lego game. You're just playing Lego here. You can assemble your queries, nesting select from wheres into select from wheres in that way. Okay, but in that case, it's a table expression in a table expression. Okay, so you see table expression in a table expression. Okay. You can do things the other way around. If you have a scalar, you can turn it into a table with one row and one column, and you just do it with a select. Select one as A is just going to build a table with a column A. It's going to infer the type and the value 1 in there. Okay, and then when you have that, that means that you can basically build this fancy query that is a table expression, select from where, that has only one row, one column, so you can use a value expression. So here you get a value, and with the select, you can again put it back in a table. So you see you have a table, you extract the number, do the multiplication, and put it again. Let me remove this, that hides the view. See, a table, convert it to a scalar, multiply, and convert it back to a table. So you see how this goes? It goes in all directions, right? Okay. Another way that you can do that, if you have several, so here it was just one, if you have several of them, and you want, for example, to put these foo bar 1 and 2, these are 4 scalars, but you want to put them as 4 cells like that, 2 by 2, with 2 columns and so on. How do you do that? You can use the values keyword. So if you say values foo1 bar 2, foo1 bar 2 is going to create a table like that. If you just do that, PostgreSQL is just going to invent column names because you didn't specify names. But if you want to specify the names, just use select star from values foo1 bar 2, which is putting in there, as table. You give a name to the table, and in parentheses, S and N would be the names of the columns. Right? It's pretty advanced, but this is the magic that allows you to just create tables dynamically. Even if they are not in the database system, you can magically, dynamically create these tables on the fly. Okay, for who is that clear? Okay. Okay, this is the last slide. This here, all of that I showed you is the advanced part, right? If you start, so first you need to master select from where, group by, having, order by, and so on, the joins. And when you do master that, the second level is to master the nesting. Tables in tables, tables in values, values in tables, values in values. And if you master that, you are the king of SQL, or the queen of SQL. Okay, yeah, and then you imagine all the possibilities and everything that you can squeeze out of your database management system. And what's really, really nice is that even if you write a very, very complex query with a lot of nesting, the system is going to optimize things. It's going to figure out how to magically find out how to make it faster, right? This is all going for free with the system. This is something you get to a lesser extent with other languages like Python or Java. Okay. Any questions to end this part? Right, that was a large one, right? It was I basically threw over several weeks SQL at you. Any questions? Anything unclear? Clarifications needed? Not in the lecture hall. On Zoom, maybe? Anybody on Zoom? No questions on Zoom? So it means you understood everything? Who understood? Who has the feeling they are good now at SQL? Not yet? Okay, then do the exercises and try to write as much SQL as you can, right? You have past exams, for example, where a typical questions is an English formulation of a query. We ask you, for example, find the person with the maximum age who did that and that, you know, and you need to write the SQL query. Then you take the answer and copy it over to the Moodle, right? So if you look at past exams, you will see plenty of questions like that. It's a very good way to train yourself with SQL. Nothing replaces practice, right? You should just not stare at slides, but you should really get a Jupyter notebook and start writing plenty of queries and playing with that. And you will see after a while, things are going to become quite intuitive. All right. Okay, well, if there is no questions, we can maybe wrap up that part. Let me look at the time. Oh, it's almost time for the break. So we might actually, maybe we can go for a break and then we'll start in the second hour database design theory, right? I think it's a well-deserved break. I sense a bit less dynamic today compared to last week. So you have deserved your break. I'll see you at 1/4 past 11 for the second hour, and then we'll go back to theory with database design theory, right? So see you after the break.